let's consider a sphere of radius 1 centered at the origin. Now we've looked at this region before, at this kind of a sphere. And I want to simply confine this sphere to the first octant for right now, just for simplicity of illustration. Okay, so let's say that here's 1 on the x-axis, 1 on the y-axis, 1 on the z-axis. Our sphere is going to be bounded by a curve here, curve here, curve here. I don't want to sketch too many contour lines so that I'll have room to label things. Now, our x-axis is going to be partitioned. So here's our delta x with xi star. In the first octant, our partition of x is going to extend from x equals 0 to x equals 1. So we can say that 0 is less than or equal to xi star less than or equal to 1, or in general this partitions the interval 0 less than or equal to x less than or equal to 1. I got a little carried away with sample points when I labeled that xi star, and actually it shouldn't have an I on it either. Okay, that should be somewhat better. There's still kind of a smudge there, but we can just kind of ignore that. Okay, so x between 0 and 1, partition, typical partition delta x with an xi star. Now, let's go ahead and first run our sample point out to the point of intersection with this curve. This curve in the xy plane, well, let's think about how we algebraically describe the region. First of all, our spherical region is x squared plus y squared plus z squared less than or equal to 1. Since we're in the first octant, we're going to assume that x is greater than 0, y is greater than 0, z is greater than 0. In the xy plane, z equals 0, so x squared plus y squared equals 1. Y would then be plus or minus the square root of 1 minus x squared. We're not going to worry about the minus because we've already specified that y is greater than or equal to 0, so that y is the square root of x squared minus 1. And that's the equation of this curve in the xy plane. So that our y values go from 0 to the square root of x squared. And it must be getting late. Let me rewrite this correctly. 1 minus x squared, not x squared minus 1. So that our delta y sub j, okay, we got a region here, delta y with y sub j star and our y can run from 0 to the square root of 1 minus x squared. So we're partitioning the integral from 0 to the square root of 1 minus x squared, and that partition will give us a sample point down here. And all we have to ask ourselves now is, okay, if I'm at the point xi star, yj star, how high can I go before I hit the surface? Well, our relationship is x squared plus y squared plus z squared less than or equal to 1. That's going to be the case until z gets too big. How big can z get? Well, if we know the coordinates x and y, we can figure out that the bounding surface is just z of xy equals the square root of 1 minus x squared minus y squared. What's bounded above by this? Well, this quarter circle in the xy plane. So I can say up here that the quarter circle described by 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to the square root of 1 minus x squared is what's bounded above by z of xy equal the square root of 1 minus x squared minus y squared. So above the point xi star yj star, which I should probably label. How high can we go? We go up here until we hit the surface. At z equals the square root of 1 minus xi star minus yj star. So we encounter the surface, and we could call that the bounding surface. The surface which bounds this region, in other words, the sphere, at z equals square root of 1 minus xi squared, xi star squared minus yj star squared. So that occurs here. The approximate three-dimensional region inside of this sphere for the delta x, delta y interval at xi star, yj star will therefore be, and I don't remember if it's the region or the volume, but the region will be approximated by this rectangular prism, very similar to the one we drew before, no real difference, except that now we can put specific numbers on this region. Not specific numbers, but symbols. We have a rectangular prism of dimensions delta x by delta y by square root of 1 minus xi star squared minus yj star squared. So our final step is to partition this interval. We do that by partitioning our z values from 0 up to top of this prism. Obtaining the typical rectangular box of dimension delta x by delta y by delta z. Let's just say that that typical box is this one right here. Let's go ahead and flesh it out and fill it in and put a surface on it. So that's going to be our typical volume increment. Delta x, delta y, delta z at xi star, yj star, zk star, our region runs from x equals 0 to 1, from y equals 0 to the square root of 1 minus x squared, and from z equals 0 up to the square root of 1 minus x squared minus y squared. Our typical z increment runs from here to here on the z-axis, and that's a delta z with zk star. So we have an interval here, a delta z interval with a typical zk star. Now any quantity that we want to integrate over this sphere can be analyzed within this small volume increment, be it a density, a moment of inertia, a probability, any of a number of quantities, perhaps even the divergence of a vector function, but we'll save that for later. So we should now be able to write the integral that corresponds to this situation. We could write the volume integral, and we could, if we choose, write the integral where we integrate a function f of x, y, z over this region. So let's do that in the next clip.